does two very nice translations and a theta z rotation. Okay, and this is a much better design. It's a hybrid design, of course, because you've got serial elements in parallel. And we'll talk about hybrid a little bit later in this lecture. But you know, this is clearly a hybrid system. Okay, and whereas this is clearly a parallel system. Okay, but they're both kinematically equivalent. They have the same degree of freedom. Okay, and this one's much nicer because it takes up much less space, which is nice. It's a planar design. Okay, this one not so much. Certainly easier to fabricate. You can use water jet, wire EDM, whatever, you know, any of these planar approaches on just a single sheet of metal. Whereas this, you might have to get this giant chunk of metal and then like hog it out in all directions, or even make different planar panels and assemble them with bolts. And so that's just a lot of steps and a lot of time and a lot of money and a lot of wasted material. You know, this one has much less weight, less material. This one also has better dynamic characteristics. This is kind of like a big giant mass on these tiny little springs. So it's square root k over m is going to be small. Its natural frequency is going to be small, whereas this one can be made, you know, better stiffness and have less mass potentially. So better dynamic characteristics. It's also thermally stable. This one, if you heat it up, it'll actually, the wires will push it up, and you might not like that. Whereas this one is really nicely thermally stable. You heat it up, and because it's all symmetric, just these bent blades will grow into their void space, and the stage will not move at all. It'll actually accommodate thermal expansions very nicely. So it's thermally stable, and there's much less parasitic error. This one, the second you actually move it with its degrees of freedom, any finite amount, it'll actually start arcing down or actually screwing down in the rotation. Whereas this one, even for large deformations, there's no parasitics. It'll just translate and it'll just rotate with no parasitics over large range. So it's actually a famous design. You know, I think Physique Instruments sells something like this as a microscopy or nano position or kind of stage to just do two translations rotation. It is over constrained because, you know, for the same reason this one is, one of these serial elements is doing the same job as the other three. So it might be better if you did a triangular stage or a hexagonal stage or something where you could just do three of those bent flexures. Right, but anyway, this one's very nice and symmetric. So, okay, so just if you design stuff with wires, which you will if you're using FACT, you can always try swapping, you know, the wires out for these kinematic equivalents. Those two I've taught you, the bent blades here and the stacked blades, tend to be really good designs in many cases. Okay, but there's like infinite kinematic equivalents, and I'll give you a library of a bunch of them that you can try. Okay, so what if now you have three bends? So say you take a blade and you bend it, two bends. You take a blade and you bend it twice, so now you have three flexure blades in series, okay? Obviously, there's no blue line that can connect the two rigid bodies, so it's not parallel. And obviously, there's three, you know, the fewest pseudo wedges you need to put in there is like at the curves, the two at the curves. So the fewest parallel elements you can chunk it into are three, and they're obviously in series, so it's a serial element, not a hybrid one. Okay, and so let's analyze, since we've chunked it into the three fewest. And of course, you could chunk it into smaller ones, but why would you do that? And if you chunk it into two small ones, you'll get the wrong answer if you analyze it, right? So best to do is chunk this into two different pseudo wedges at the corners, right, or the bends. And then you could add the freedom spaces, or you could find what's common between all these three. And if you stare at that forever, you'll find there's really nothing common between the three. The moments don't point in the same direction. And you could say, well, this dashed line is common between these two, but yeah, it's not on this one, and vice versa. So there's nothing. It's actually 6 degrees of freedom. And it turns out anything, no matter how many bends you put in it, once you get a flexure blade, you bend it more than once. Two creases, or if it's just continually bending like a curve, then you're going to get 6 degrees of freedom. It won't provide any constraint. Okay, so So again, this one, to analyze it, you'd have to chunk it into wedges so that each thing in between is filled with blue, but as few wedges as possible, so you can still fill the whole thing with blue, and then analyze it, and you'll find, for the same logic as this, that this final thing has 6 degrees of freedom. It doesn't constrain it at all. Okay, in theory, or the stiffness in those 6 directions is comparable and very small. Okay. So what if you take a wire and bend it, a bent wire, and you find, well, this is obviously not a parallel thing. It's obvious how you chunk it up. It's a serial thing with 2 parallel elements, 2 wires in parallel, in series, and you find what's common between their constraint spaces, which is just 2 blue lines. Well, you might say, well, the dot is common, but like a dot isn't anything, right? It's got to be a blue line, an orange line, or a moment that's common, right? So there's nothing common there. There's nothing common. So it has 6 degrees of freedom. And by the same token, if you take a wire and curve it, again, you'd have to break this up into different little pseudo modules where one blue line can fit in it. So you stack just a bunch of blue lines in series, and you'll find the same thing. If you add their freedom space or find what's common, you'll find the freedom space is just 6 degrees of freedom and the constraint space is empty. Okay? And same thing, these are serpentine flexures. They're very common in MEMS, right? They just have basically a bunch of wires, in series. And by the same token, they're 6 degrees of freedom. Now, I don't know why this is common in MEMS. I think I do know why. It's because a lot of people that design MEMS don't necessarily take the time to understand how to design flexures, and they see other people doing it, so they just use it. And so it's really not a good design. First of all, it wastes a lot of material. I suppose it's compact. It can get large range, and it does provide some stiffness without providing constraint. But there's a lot of mass that can flap around, so it's in many ways behaves as if it's under constrained. It's not symmetric. There's no plane about which it's symmetric, so there's parasitic errors, and it's kind of a mess, right? So it's not, even though technically no element can be exactly or over constrained, and then by the same token, no element by itself can be under constrained or not under, not under constrained, no element, even serial and hybrid, can be under constrained, right? So because there's no intermediate body in between for it to have a redundant degree of freedom to be vibrated. But however, there's pseudo bodies in between, and so they will behave as they're under constrained. Let me make this point a little more solid. And I may make this a little more solid later as well, but let me just review here. So no element, parallel, serial, or hybrid, as I've said before, can be over-constrained. It just has an order of constraint. So you consider them by themselves as an exact constraint element with a certain order of constraint, right? Well, certainly no parallel element can be under-constrained because it's a parallel element. Nothing with the word parallel in it can be under-constrained, okay? But serial and hybrid elements, you'd think, serial and hybrid systems certainly can be under-constrained, but serial elements actually cannot be, or hybrid, right? And the reason is because they're compliant over their whole geometry. They don't have rigid bodies or those rectangles in the schematic in their geometry. They connect at points, lines, and curves. So they don't have masses that can be considered to be masses with redundant degrees of freedom. So now I know in practice, they obviously have mass, and you can consider a number of point masses, and it would behave if you do it messy enough, like a serpentine flexure held this fixed with respect to that. These guys could flop with all kinds of redundant degrees of freedom, and it would start exhibiting the downsides of under constraint. But so far as theory goes, because there's technically no rigid body, just these two, in here, then there's no rigid bodies to vibrate and or to have redundant degrees of freedom. And so just like technically elements can be over constraint, behave over constraint like, and you can do things to them to make them behave less over constraint. In theory, we assume they're never over constraint, they just have orders of constraint, right? But in the case of serial and hybrid elements, they can technically kind of behave as if they're under constraint, and there's things you can do to get rid of that. But just know, according to theory, we don't normally consider them as ever being able to be under constrained, okay? Because they don't have intermediate rigid bodies. Okay, I'll probably talk about that a bit more, but that's important. So no element by itself, either parallel, hybrid, or serial, is ever going to be considered, in theory, over constrained. And none of them, even the serial and hybrid ones, will also be considered in and of themselves under constrained. Okay, they're not under constrained, and they are exactly constrained in theory always. Okay, but just know in reality that they can behave as, like a blade's going to be more over constrained than a wire. You'll see more over constraint negatives with it because it's got more blue lines in it that are redundant. And this will act much more under constrained in reality than, say, this one, because there's a lot of mass that actually can have redundant degrees of freedom and bounce around if you hold this and this fixed. Okay? Okay. But going back to dissing on serpentine flexures, they're really not good. There's not planes of symmetry. They're parasitic errors. They do behave as if they're under constrained, and it's just sloppy, bad flexure design to use them. Okay? Maybe they could be good if you need to be super compact and there's no other solution, but there's always another solution. So just don't use them. Okay? Okay, and then the traditional spring. Remember coiled springs? That's, anyone who thinks of a spring thinks of this. Who's not or even mechanical engineers. Anyone thinks of this, thinks the word spring, if they're not thinking of a season, they're going to think of this, okay? So this is where the schematic comes from of the zigzag spring, right? They're thinking of this coil spring. But you ever ask yourself, well, what is the constraint of this? Well, this is essentially just a bunch of wires kind of in series. Okay, as they're kind of wrapping and curving around, you'd have to break in a number of wedges all the way up, so it's just a single wire kind of connects them. It would be a good way to think about it. And so, sure enough, it's 6 degrees of freedom. It really just adds stiffness without, first of all, this is an interesting element. It's largely linear stiffness. So if you plot force versus displacement, it'll be linear for a good chunk of time, and it gets a pretty good range without yielding. And it just kind of adds stiffness in all directions without really constraining anything. So that's why it's kind of popular. Because what most rigid mechanism designers do is they design a rigid mechanism, and then if they want stiffness or storing strain energy capability, they'll just grab a coiled spring and chuck it in there. Which, again, I don't really consider that to be a compliant mechanism. That's just a rigid mechanism with a coiled spring in it. But some people would disagree and be like, well, there's something compliant in there, so it's a compliant mechanism. Well, anyway, we're just splitting hairs with definitions. Okay, but anyway, this is, now you can analyze this, and this is a serial element, okay? Not a parallel element. Okay, so this is something my professor at MIT, Martin Culpepper, did with Chris DiBiasio and actually some other students in the lab. Is he sought out to design a flexure-based 6-axis positioner. Okay, he called it the hex flex. Being able to move something in 6 axes, the 3 rotations, 3 translations, however you want, and with closed loop control, is kind of like a holy grail with high precision. In his day, and when he was working on this, and to get the precision, comparable precision, you could there's systems, multi-million-dollar systems that did this with magnetic or air bearing, kind of things, machines that took up entire rooms, right, to get the precision. But he realized, look, if I just stick these single bent wires onto this. So here's the ground, here's the bent wire, and here's the stage, right? And if I put 6 of them, 1, 2, 3, 4, 5, 6, okay, then you can design this. Then it is designed so that this stage now can move with the 6 degrees of freedom, without much constraint. They just have some stiffness on it. But since they're flexures deforming, they have very high precision, and this thing is super cheap to make. I mean, this was made on a wire EDM, but for a couple $100, I guess, you can, with a tiny little mechanism about this size, you can have a machine that does what these giant multi-million-dollar machines can do. So, a pretty big breakthrough. And you put like magnets on these tabs and actuate it from below, so you could actuate and drive it and have sensors and stuff to have it be fully closed loop and that kind of thing. So they did some great work a number of years ago on that. But this is a great case study. First of all, this is not, a lot of old flexure designers would consider this a parallel system because it's just a bunch of flexures in parallel, right? But fact wouldn't be true if you called it that. It's actually a hybrid system because, as you know, this is a serial element, and it is now in parallel. 6. It's like if you drew the schematic of it, you would draw. Well, here, let's draw the schematic of it. Okay. You would draw. So I'm not going to draw it on top of it, but you would draw, here's a parallel spring and then a dot, and there's a parallel spring, okay, and then the ground, and then here's the stage, right, where this parallel spring is one of the wires, and this parallel spring is the other wire that's bent, and this dot is the line here. Or sorry, this is actually a point in reality too. Remember how in reality you can get a point, line, or curve? This is a point because it's just two wires connecting together at a point. The bent blade one is a line, and then the two circular hyperboloid ones on top of each other, those are curves that meet. But in the schematic line, you just put a dot, whether it is or not. So that you got your one serial thing, and then you'd get another serial thing, another serial thing, another serial thing, another serial thing, and then another serial thing. That would be the schematic of it. The ground, which is the outer thing, to the stage, which is this one. Okay, and then you've got your 6 serial things in parallel. And since there are serial things in parallel, it's a hybrid system according to fact. Okay, and honestly, you could have gotten the freedom space with just one of them. Okay, if you had just put one bent wire on it, it would have gotten 6 degrees of freedom. Problem is it's not nice and symmetric, and there'll be parasitic errors, and it's harder to control. Right? If you have if you make it axisymmetric and nice and symmetric like we've done here, then you're going to get rid of parasitic errors and make it much easier to control. The question is, you might say, well, this is over-constrained though, right? Because we're doing the same job 6 times. Okay, by putting this on, this is doing some job, and now we just did the same job 6 times, and so it's over-constrained by 5. Well, you'd be wrong. And here's one final caveat about over-constraint, is that, if a flexure doesn't do anything, then if you repeat it, if you repeat it multiple times, it's still, nothing is doing anything. So nothing's competing. There's not going to be stress buildup. There's not going to be over-constraint. There's not going to be issues. It's like if you put, 6 grad students on a project, they're not going to compete if none of them are doing anything, if they're not working, right? It's only if they're all trying to do the same job and they're actually doing a job that they might butt heads, right? So it's yes, even though technically you have a redundant constraint that's doing the same job, because that job is nothing, it's not doing the same job. So that's how you think about it. This is not over constrained, and it's thermally stable. You heat it up and it's not going to move anywhere. And it's symmetric with nice parasitic error. So it's a nice design, but it's not parallel. It's hybrid. Okay, according to fact anyway, if fact's going to work. Okay, so now remember, let's look at this one. Okay, and remember, right off in your head, you're like, oh, look, check it out. This is a blade, that's a nub, and that's a blade in series. So you say, oh, it's a serial thing. Well, don't necessarily jump to that. What you want to do is, again, draw your blue lines that connect the 2 rigid bodies that pass entirely through the geometry and not exit it, and find out what happens. And you might recall when we did that, we get all these blue lines that kind of go through the neck there, and you have these big triangular sections that can't be filled blue from the last lecture. And so I said, so you see, or from, I don't know how many lectures ago, but you said, and so you see it's not parallel. Once you know it's not parallel, now you know it's serial, because now you can see, well, the fewest things to chunk it into is put like a fake rigid body there, a fake rigid body there, and then the rigid body's there, and it can be chunked into 3 different things: a blade, a nub, and a blade, right? Now, if you were analyzing this, okay, let me tell you why it's important. This is kind of a trick question, okay, because someone might say, okay, well, this might be serial, it's not parallel, but let's use the parallel rules to analyze its constraint and freedom space. You could say, well, obviously, if we do the parallel rules, draw the blue lines through here and fill it up, it would be a disk of blue lines. And they say that, that's the constraint space and its freedom space. You could look up what it is. And in this case, it happens to coincidentally be true. This is the constraint space. This is a disk of blue lines located there. But that's very dangerous. Don't think that because that rule worked. Don't think that because you tried to apply the parallel condition to this by drawing the blue lines and it failed, you're like, okay, well, now I know it's serial, but now we're going to use those blue lines and synthesize, and linearly combine them to get the constraint space. It works for this one, but that's just a coincidence. Okay, there are many examples I can give you where if you do that, like for instance at the beginning, let me go back here. Okay. Okay, like this one. If you said, okay, let's draw the blue lines that satisfy the parallel condition here, the only blue line that goes from this body to that body and goes entirely through without exiting it is this one. So you say, well, because there's empty spaces, it's not parallel, it's serial. But then you say, well, then obviously the constraint space of this is just the blue line. That would be wrong. That's not correct. Okay, this does not just get a blue line constraint space. To analyze this appropriately, you'd want to find the constraint space of this one and the constraint space of this one, which is that, right? And then you would want to find, and not just the blue, but it also has orange lines and black lines, and find what's common between both. And it's not, there is the blue line that's common between both, but there's also a pure moment and a pure moment and an orange wrench along this line too. So you really need to don't just take the blue lines that satisfy the parallel condition and say it's the constraint space. You will be wrong, okay? You need to take the constraint space of the parallel modules and find what's common, or take their freedom space and linearly combine them. Okay? All right, so let's go back. Okay, so let's show here. Okay, so here we are. Okay, so what we do is we don't just draw the blue lines and say, oh, the answer is a disk. If we did that, we'd have dumb luck because we'd be right, but we did it for the wrong reasons, right? So the correct thing to do is look at the constraint space of these, which is this blue plane with the black thing. Let's look at the constraint space of this, which is a disk, or sorry, not a disk, a sphere. The nub flexure. Put them all on top of each other where they belong and find what's common. Okay, so you can say, does everything have a moment in this direction? Well, these two do, but this one doesn't. Okay. All right. What blue ones are common? Well, it looks like a disk is actually common. Okay, so you can see the thing that's common is that. And by the way, you should also consider the orange lines too, of which there are none in this example. There's no orange lines in this constraint space or black lines. There's no orange lines in this space. So we've considered the full thing. But if you're doing this, you have to consider everything. Find out what's common, and you'll find this disk. Okay? And that just coincidentally happened to be the same constraint space as if we drew the blue lines from the parallel thing. Okay? But again, don't do that. Always follow this approach. Add freedom spaces in series, or find constraint spaces that are common that are in series. Okay? Find out what is common between constraint spaces in series. That will get you the correct freedom constraint space every time. Okay? Just use that trick of finding blue lines that connect the things and don't exit them and try and fill it to identify whether it's parallel or serial. Once it fails the parallel test, throw those lines out and don't use them again. You chunk it in to find the fewest number of parallel elements that are stacked in series and then apply this approach. And you'll get the right answer every time. Okay? So this one's freedom space is this. Okay? So you can see there's a bunch of screws in here, but if we overlay the red and the black, you can see, sure enough, you get every rotation that passes through there, including this rotation, which is the most obvious one, and then every rotation on this plane, which is the torsion and the bending, as well as the translation, and then a bunch of screws. Okay? Okay, so this one, and by the way, because it's a 6 DOF, or sorry, since it's 4 DOF, that means its order of constraint is 2. Okay, so it's a serial element with an order of constraint of 2. So this is why, you know, I've seen some Dutch flexure designers. The Dutch are some of the best flexure designers in the world, by the way. You know, they had issues putting, you know, if you just put 2 parallel blades together, like just take 2 blades like this and stick them in parallel on a parallel guide mechanism. Remember, when we analyzed that, we showed it has 1 degree of freedom, and which is a translation. That's the whole point in this direction. Which means it should have 5 non-redundant constraints. But there was an order of constraint of 3 from each. So if you put the 2 together, you're over-constrained by 1. Well, what I believe is the Dutch that discovered it, at least that's the first I've seen, is they cut these things out so you have the little nub there. And now it turns this into a serial element and with an order of constraint of 2. So now it's 2 plus 3 is 5, and now it actually works. And this is really nice, because if you're taking 2 parallel things and bolting them together, having to assemble it, you know, you have all sorts of issues with over-constraint, bifurcation, non-linearities, and it can be a mess. So this fixes the whole thing and makes it a nice design. Okay, you could also do, you know, that bow tie, that V-shaped blade thing on one side. That would work nicely too. Okay. And if you did that, then it would be a parallel system. This, by the way, is also hybrid, right? Because you've got a serial element in parallel with a parallel element, and that makes it hybrid, technically. Whereas, interestingly enough, if you did that V-shaped flexure blade, so you didn't have these corners, 1, you'd save mass, and 2, it would now be a parallel system, because it would be 2 parallel elements in parallel. That would be a parallel system. Okay, so some interesting rules and interesting classification of the names. But this, if I asked you on an exam, you'd say this is a hybrid system. Okay. Okay, so here is another flexure system that's interesting. Like, how do you analyze this? You might think, well, this might be hybrid, because it's like, oh my goodness, you've got, you know, a wire is parallel, and it's like a bunch of wires in parallel, and then you've got this serial, you know, system right here, and then, or sorry, element right here, and then you've got all these parallel things here, and here's the 2 rigid bodies. But this is a, you know, of course you ask yourself, is this a parallel element? And the answer is absolutely not. There's not a single blue line that can connect that to that without exiting the geometry. So it's definitely not parallel. Then the question is it serial or hybrid? Well, again, this one's a little tricky. You might think, oh, it's a hybrid element, but you'd be wrong, because what you do is you chunk it into, say, a rigid thing here. Now you've got just a bunch of parallel springs in parallel. So this makes kind of a parallel system module. And then this is a serial element. And then you put another rigid chunk there, and again, it's just another parallel module. So you basically, if you drew the schematic of this, it'd be like, and say you added your rigid stage, you know, just to, it's easier to identify serial systems than serial elements. So anytime you have like a pseudo stage, you can add a rigid stage there, and you would find parallel system in series with a serial element in series with a parallel system. That's a serial system. And it would be, therefore, because there's everything joins at a point, in this case a line or a curve, not the case here, this would definitely be a serial element, which is why I'm lecturing on it in the serial element lecture section here, obviously. Okay, so how do you find its constraint and freedom space? Well, you say, this system gets this constraint space. This system gets this constraint, and you add all those lines up together and you get this with the moment. And then you get this one, and you put it all together, and you find what's common between them all three. Well, you find there's actually no blue lines that are common between all three. And that's obvious because there's no blue lines in this that are common between these two even. So there's no